Okay, let me share my screen. Okay. So my screen is visible to you, I hope.
Yes.
Okay. Okay, so I would say that today let us just wind up the remaining things about recursion. Of course, I have near the end of yesterday's class, somebody told me something about circular permutations. Maybe I will come to that little later near the end. Okay, so the last little bit of recursion. So you have seen several examples like bin search, 0 to 9. This in turn calls bin search, let's say 0 to 5, or maybe 4. This may be calling bin search, maybe 2 to 3, 3 to 4, something like that. Okay. So a call, and this is definitely called by main. Okay. So a function like main is making a call. It in turn makes a call of the same function. This in turn makes a call of the same function, and so on. And this is just a case of a single function, but I may have something like this. Main calling a function A on some parameters. This is calling B on certain parameters. B itself calls A certain parameters. B again, and this way. Eventually, there should be a way to stop this recursion, but that is fine. The question is, at any point of time, you can see many, for example, if I do this binary search thing, many instances are active. Okay. So many instances are active. Okay. Okay, so active, only one instance is doing something. In fact, this is the last called instance is doing some computation. The last one. Others are simply waiting. Okay, so that is the general thing. So when this bin search 09 calls bin search 04, this is doing some kind of work, and this is simply waiting for some value to be returned by this call. Likewise, this, depending upon the key, may make a call bin search 3, 4. And when this is doing some computations like 3 plus 4 by 2 and all that stuff, at that point of time, this is waiting for this. This is also waiting for this, and so on. Okay. I assume that you have a single processor machine and there is nothing, no parallel processing and that kind of stuff involved in your code. It's a plain, simple, sequential C code. Okay. The question is, how does the runtime system, or for that matter, the compiler, keep track of all these different instances of the same function? Okay, so that's a question that needs to be solved for a compiler designer, in order that recursion can be implemented successfully in a modern machine or in any computer for that matter. So the basic data structure that the compiler, or for that matter the runtime system uses is called a recursion stack. Okay. So whenever you call, for example, main, okay, so let me do it this way. Whenever you call main, so this may be main, and main has some local variables. Okay. And of course, I assume that there are no global variables, but some global variables should also be maintained somewhere. Let's not worry too much about global variables. So maybe main is calling bin search 09. Okay. So here, this invocation of bin search has some parameters like L equal to 0, R equal to 9. It also has some local variable M, which is computed as 0 plus 9 by 2, that is 4. Okay. And this may actually involve many other local variables. So it's something like this. Now, suppose based upon the comparison result, it's something like bin search 10, 5, 4, 4, no, not 5 to 9 is called. Okay. So for this invocation of bin search, the left end is 5, right end is 9, and it computes the middle element as 5 plus 9 by 2, that is 7. Okay, and this keeps on happening. Okay, so this may again call something like this, bin search 5 to 7. Okay, so L is 5, R is 7, M is computed as 6, and so on. This thing keeps on happening. Now, different invocations of the same function, this is bin search, this is bin search, this is bin search, they have their own local variables and parameters. For example, L is 5 for this, L is 5 for this, whereas L is 0 for this. R is 9 for this, R is 9 for this, but R is 7 for this. And M, this is computed as 4, this is computed as 7, this is computed as 6, and so on. Okay. So, in order that the different invocations, okay, work properly, so each, you'd say, item in the stack stores several things, among many other things. This may be this, local variables, and maybe something like return address, possibly some other things. Okay. So these things is called an activation record. Okay.
Sir, whatever the stack stores is called the activation record.
No, each I would say these are the part of the activation record for this call. This part is called, this is the activation record of this call. Okay. And of course, this bin search 5,7, this need not be stored. This is just for illustration. This thing did not be stored. This is just for our understanding. This is not part of the activation record. Okay. But also some return address should be there. So it will compute a value and it will return that thing to it, a local variable or somewhere here. So where that thing will go, it should also specify that return address. And when this finishes, it returns something, not just a value, but where it will go to. Okay, from which point onward, it will start working. This is done. This is returning from which point onward. What is the return value, and what is from where this keeps on starting. Okay. So all these things are part of the activation record.
So
Whatever it is called.
LNR is local variable or LNR is function argument?
LNR are parameters, right?
Yes.
But
So,
parameters with I would say in
so
all.
only one local variable, that is mid, m.
Yeah. But any parameter that you pass to a function, they essentially behave like local variables.
Okay.
Right?
Yes.
Okay. Parameters are like local variables. They are always passed via copying. Right. So whatever L and R is here, and whenever this calls, the values are copied, and this L and R, they behave like local variables, and they have some values which have nothing to do with the caller's L and R values. Okay. So only some specific things that a function needs that can be pushed as an activation record to the top of the stack. And when that recursive call returns, okay, this entire activation record, this can now be completely taken out of the stack. If there is a return value, that should be passed to the caller function, this activation record, and this so-called control of this function will go to wherever just after where this recursive call was made. Okay. So this is how basically recursion works. So this kind of data structure is called a stack because it's like a stack of plates. So you can always access only the top. You can add a new plate on the top of the stack, and if you want to take out one element, it should be from the top. Okay. And you are making recursive more and more recursive calls, so the stack eventually grows and grows and grows. And when the calls return, the top elements are one by one removed. Okay, so this is how it works. So there is no conflict of this L, R, and M values for this instance of this call with the L, R, and M values for other instances of the call. So they are separately maintained. Okay, so whenever this refers to L, this call, it means this L, not this L or this L, or if there are some other recursive calls, not those things. Okay. Similarly, when this considers this M, it means this private value of M, not this M that will in future come to existence, or this M. Okay. So each activation or call of a function is associated with storing the values of the local variables, which includes the parameters. Okay. And you just convince yourself that the body of the function, which is whatever it is going to do with these local variables, that need not be copied. That's a fixed set of instructions. Okay, so for example, compute M as L plus R by 2. So it is that piece of instruction, or that piece of sequence of instructions, that sequence of instructions need not be copied, although it is the same. Only thing, the meaning of L, R, and M, they will change from call to call. Right. And similarly, return address may be somewhere in that body of that call. Okay. So we all want to do, what we all want to do is to store the local variables, return address, maybe return value and similar things. Nothing more than that. The entire code of the function need not be copied to the stack as a part of the activation record. Okay. There may be a single copy of that function and that's good enough. Okay.
Sir, is this stack structure followed for any type of function calls, like, or
Yes.
is it unique
Yes,
for
yes.
recursion?
Yes, any function call. Look at, I already have main here. Main calls binary search. Binary search may call, yeah, it may be something like this, even if it is not recursive.
If we call a function from one function and then that function calls another function, then also these activation records are.
Yes, yes, exactly the same way it happens. Even if the main calls F1, F1 calls F2, F2 calls F2, these are all different functions. There is no recursion involved here, but still this recursion stack or call stack you may call, this is organized in the same way. So there is nothing specific we are doing about recursion, but recursion is important in the sense that all the calls are using the same local variables. I mean, a set of local variables with the same name, and therefore the resolution of L, R, M, things like this, that depends on the activation record of the corresponding function. Okay. So main calls F1, F1 calls F2, F2 calls F3. That's anyway possible. And F1, F2, F3 may or may not share any common variable, local variable name. But anyway, it has its own bag of local variables. F2 also has its own bag of local variables. F3 has its own bag of local variables, and so on. Main also has something.
Sir.
Okay. Yeah.
So how will the stack look like for multiple branch recursive call, like for finding Fibonacci number?
Yeah, I will come to that. At any one point of time, exactly one thing is getting executed, right? So what happens if you make two recursive calls, as in Fibonacci number, or for that matter, in the case of let's say permutation generators, Tower of Hanoi, and things like that. Okay, you make two recursive calls. Okay, but they are executed not in parallel, but in sequence, one after another. Okay, making parallel calls is another possibility, but that requires special constructs. Okay, which is too much to deal with in this course. Okay, creating new processes or for threads and giving task for each child or created thread. Okay, but this is things we will assume that there is a single process running, and therefore at any point of time, exactly one function is doing something, and other active functions may be just waiting in the activation queue, in the activation stack or recursion stack or call stack, whatever you call. Okay, so I will demonstrate how it works. Okay, of course we have already seen a way of viewing recursive computation, that is by recursion tree. Now we will see how
Sir, so this stack is actually a snapshot in time, right? Of the stack, like, at any point of time.
yes, in a sense, yeah. At any point of time, main calls what, and that what calls what two calls what three. Whatever is the current sequence of calls starting from main, that is stored in the call stack. Okay, at the top, the most recent call. At the bottom, the I would say the most distant call. Okay. So here what I do, first I illustrate using a simple thing, factorial. So the code is something like this. Okay. I do not remember where I am stopping, maybe something like this. It's something factorial int n. It will return an integer. If n is 0, return 1. Otherwise, return n star factorial n minus 1. Of course, I assume that n is positive in order to ensure that I can have unsigned int here, but anyway. Okay. So if I want to call factorial, let's say fact 7, this is not satisfied. So this will call fact 6. This will call fact 5. This will call factorial 4. This will call factorial 3. This will call factorial 2. This will call factorial 1. And I do not remember what on exactly which code this is based. Maybe on n equal to 0 or n less than equal to 1, whatever. Anyway, with respect to this code, this will call fact 0. So this will not make any further calls. Okay. But instead it will return 1 to fact 1, this invocation. Then it will multiply 1 by this return value and return 1 to this. Then this will multiply this return value 1 with 2, will return 2. This will return 6. This will return 24 and so on. Okay. So let us see how this stack grows and shrinks during this recursive sequence of calls. Okay. So main. Okay, factorial 6 it is calling. So on the top of this stack, the activation record for this particular call is pushed. There is only one variable n, local variable. It's actually a parameter, but it's typically used as a local variable. So n equal to 6, that is stored. That is the meaning of n for this invocation of factorial 6, the invocation of factorial. Then it calls factorial 5. The moment this call is set successful, another thing is pushed on the top of the stack. So factorial 5. For this instance of factorial, n is 5. This has nothing to do with this n. Okay, they're completely different things and stored in different areas. And this is a part of the activation record for this factorial 6. This is a part of the activation record for this. Okay, so it will call factorial 4. So factorial 4, factorial 3, factorial 2, factorial 1, calling factorial 0. So now this is n equal to 0, return 1. Okay, so this will simply return 1. And this return value will come to here, not to any other thing. Okay. When the top goes, okay, the next thing becomes the top and the control goes there. Okay. So got the value 1, so it multiplies that by 1, as I have done here. 1 multiplied by 1, product is 1, then it will return product, the product 1 to its caller. So this 1 will come to this next one. Got value 1 multiplied by 2, okay, and return the product 2 to the caller function. So 2 will come here, got value 2. This will multiply by 3. The product is 6, so this is returned. This will go to this, and so on. This will keep on happening. Multiply 24, multiply by 24, 120 will go here. So eventually it will factorial 6 multiply by 120, returning product 720. So eventually the main gets the value 720. Okay. But this is the case of a single recursion. one invocation calling another invocation. What happens if I have multiple invocations? Okay, so that is illustrated. So this animation is done. So I will start a second animation. Fibonacci. Okay. So now maybe I just write the code for this. This also will return int Fibonacci int n. If n equal to 0, return 0. If n equal to 1, return 1. Else return f n minus 1 plus f n minus 2. Okay. So I can view this total amount of computation as a tree, maybe fib 4. This calls fib 3, fib 2. This calls fib 2, fib 1. This fib 2, x2 calls fib 1, fib 0. And this also fib 1, fib 0. Okay. So you can view the total amount of computation in the form of this tree. In reality, what will happen whenever you call fib 4, it will call fib 3, this will call fib 2, this will call fib 1. So this stack will store fib 4, fib 3, fib 2, fib 1. Okay. But fib 1 does not make any further recursive call, so it will return the value 1. Then the second recursive call on f0 is made here. So at that point of time, the stack will look like fib 4, fib 3, fib 2, fib 0. When this returns, it will compute the value of fib 2, return it. And then this makes a second recursion this. So at that point of time, the stack will store 4, fib 3, fib 4, fib 3, fib 1. Okay, and so on. So this is how this tree is essentially, you may call it constructed or whatever, gradually, one by one. So let us see. So this is clear, right? First 4, 3, 2, 1, then 4, 3, 2, 0, and then 4, 3, 2, and then 4, 3, 1. Then eventually this will return. So 4, 2, 4, 2, 1, 4, 2, 4, 2, 0 eventually. Okay. Anyway, let us see how this stack grows and shrinks. Okay, in the Fibonacci example, in the factorial example, stack grew, and then shrank. But now it may grow and shrink with respect to time. So let's see what happens. Oops, with Fibonacci 7, it will be a long thing. Okay, let's see. Let's run it for some time. So Fibonacci 7, okay, n equal to 7. Okay, this n value, this is like a local variable. So this is 7 for this call. Now this will make the first recursive call fib 6. So this is created. This first recursive call fib 5, fib 4, fib 3, fib 2, fib 1. Now, since n is 1, it will not make any further recursive calls. Instead, it will simply return the value 1. Okay. Up to this point, the stack kept on growing. Okay, but now it's going to shrink. Okay, so 1 will come here as the return value of the first call. Okay, got fib1 equal to 1. Then this fib2 has some more unfinished business. It will have to call fn minus 2, that is f0. So it will make the second recursive call fib0. So once again the stack will grow. And this will not make any further recursive calls. Instead, it will simply return 0. So this will got fib0 equal to 0. Then it will add these two return values 1 and 0, and it will return the sum 1. So this will get fib2 equal to 1. But then it will also have to make a second recursive call on n equal to 1, 3 minus 2. Okay. So second recursive call is on fib1. So another thing will, again, the stack grows. Okay. This will return 1 without making further recursive calls. So this is fib1 equal to 1. Then it will add up these two return values 1 and 1, and it will return the sum 2 to this invocation fib4. Okay. Then this will make a second recursive call on fib2. Okay. And this will keep on going like this. Eventually, fib4 will get the value fib2 equal to 1. So it will add 2 and 1 and return 3 to the caller. Okay. Again, this will make a second recursive call fib3. So once again, the stack will grow. Eventually, this will get the value fib3 equal to 2. It will add 3 and 2, return 5 to this. Okay. So this is how it keeps on going. Then once again, this fib6 will make a second recursive call on fib4. So once again, for some point of time, the stack will grow and shrink on the top of it. And eventually it will get some value, add it up, and will return to fib7. Okay. So this is how recursion is handled. Okay. So by storing the values of the local variables and parameters, and where I return the value. Okay, things like that. So these are called activation record, and storing just this minimal amount of information is good enough. You do not have to store the entire code of the function, the body of the function, the compiled body of the function in an activation record. That may be a common thing. Everybody may share that code. Okay. Only the interpretation of these local values, n, m, l, r, whatever you are using, they should be clearly defined by each invocation. Yeah. So let me know. Okay. So it's not exactly, I would say, very much important for understanding how to write recursive programs, but maybe this exposition gives you an idea how machines work in reality. Okay. In, I would say, 1950s, there was one programming language which is still used nowadays till today, that is called Fortran. The initial version of Fortran did not support recursion. Okay. So these kind of concepts, okay. So for example, in Fortran, what happened was that fib has just one, I would say, body, and whenever you make a call on n equal to 7, you just make n equal to 7. There is nothing called activation records, nothing called stacks and all that stuff. It's just one instance of fib and one instance of this n and so on. Okay. So in 1950s, we did not know how to handle recursion. Okay. Later, in mid 1960s, I would say, a person called Charles Anthony Richard Hoare, he designed a sorting algorithm called quicksort. And that's a very recursive one. I hope we will have some time to look at this quicksort, merge sort, some recursive sorting algorithms. And he was so enthusiastic about this implementation of recursion, so he himself wrote a compiler for some language like Algol. Okay, but from that point onward, most of the I would say high-level programming languages that came, they supported recursion. And once you understand this call stack or recursion stack, implementing recursion is not really any issue at all. Okay. And nowadays, of course, the current version of Fortran, which is still in use, it definitely supports recursion. Okay. So that's an important thing. Not exactly very important in terms of programming point of view, but it's a good idea to have some knowledge of how computers can handle recursion. Okay, so this leaves us with a few other miscellaneous topics. Maybe I will quickly browse through this, but let me know, do you have any I would say queries about this?
Sir, if we send a variable by reference, pass by reference, then will it be added to the activation stack of the current calls?
Yeah, everything will be added. Look, there is not, I would say, there is nothing called pass by reference. You essentially pass an address, and whatever the name that address has, under that name, a copy of that address is stored in the activation record. That is C's peculiarity. Everything is called by value. But as I mentioned earlier, if you pass an address, a copy of that address is created. Okay. But whatever copy it is, if it is an address and I want to access whatever is there in that address, it does not matter what is, it does not matter which copy that is. That is the reason array elements are visible inside a function call. This will be clearer when we later see that arrays are essentially addresses. And addresses are essentially pointers. So arrays and pointers are essentially the same thing. Okay. There are some minor restrictions, but anyway. Yeah. So everything is called by value. There is nothing called call by reference. You can pass an address, a copy of that address will go to a called function. But if you have a copy on your hard drive, on a piece of paper, whatever, the copies are different of the same address, but they are all pointing to the same location. So it does not matter using which copy you are trying to access that memory. Your hard drive thing or something written on a piece of paper or whatever. If it is room number 1, 2, 3, CSE department, IIT Kharagpur, wherever it is written, it will essentially point to the same location. The copies are different, perhaps. Yeah, so that's the idea. Yeah, but I will just mention something that although this and this and this and this and these are different, they have different meanings for different invocations, but there is something that can be shared. I will just mention, if you are interested, you can look at our slides or look at books. So,
Sir,
yeah, tell.
so I have a question regarding factorial one.
Mm-hmm.
Sir, if method 1, if we use like a simple for loop, and method 2, if we use recursion for finding factorial, which one will be like more efficient for?
For factorial, of course, they are more or less the same. Of course, function call has an overhead because you have managed that activation record and all that stuff. So recursive call may be slightly slow, but if you do this Fibonacci thing, it's always, I would say, it's much faster to write an iterative code. So it may seem that recursion is not very useful for computing Fibonacci numbers. That is true. But if you want to solve some other problem, that is why I took examples of difficult problems which are very difficult to solve without recursion. One is that Tower of Hanoi problem. Did anybody say anything?
क्या
जम्मू में देखो फ्री आना के लोग वैक्सीन लगवा के आओ
वो तो हम लोग जब कैंपस जाएंगे तो यही होगा बिना वैक्सीन के वो घुसने नहीं देंगे
Okay. Yeah, so what was I asking? What was I talking about? Yeah. So there are examples like those Tower of Hanoi problem or permutation generation problem. These can be very effectively handled by recursion. In fact, if time permits, this is actually a curtailed semester, I don't know. Near the end of this course, we usually teach you something about the stacks and queues. And therefore, you see that wherever you make recursive calls, you are essentially using a system maintained stack, which may be called the call stack. Actually, call stack is better than recursion stack because it's independent of recursion. For any kind of calling, this happens. In any case, you can write your own version of this call stack, and you can replace every recursive function to a iterative function, to an iterative function or iterative computation using your own stack. So that may be a reason why you should also understand how this call stack work. If you yourself do not have an option of using recursion, then implement your own stack, okay, and simulate recursion, as these examples illustrate. Okay. So, but anyway, then you have to take care of your activation records and all that stuff. Not going to be a very easy thing in general. Okay. Yeah. So recursion actually helps. And not only that, it helps in writing your code. I would say it is the ultimate thing about programming. In the sense that something or some computational problem is solvable in a very loose sense, if and only if you can write a recursive function for it. Now, this is a very, very deep result beyond, I would say, miles away from the scope of this course, but this is a fact. This is reality. Something is computable if and only if you can write a recursive code for it. If you cannot write a recursive code for it, then you cannot compute it in any other manner. Anyway, but this is a very, very deep result, well beyond the scope of this course. Okay, let us come back to programming issues. So far, we have seen some variables, local variables, which are not shared between invocations, but you can define a local variable using the keyword static. For example, I can say static int n equal to 5, or maybe x equal to 5. And I have a function where this is defined like this. Okay. So when this function is invoked for the first time, x is initialized to 5. And here maybe you make x plus plus. Okay, so x becomes 6 now. Now you make, let's say this function has name f, whatever. Now you make a recursive call. Then this will once again try to initialize x to 5, but no, because this is a static variable. This instance of x is shared across all invocations. It is initialized just once. When you make a call, x will no longer be initialized to 5. Instead, it will continue to see the value 6. Okay, so static variables are shared. What am I writing? Shared by whom? Different invocations of the same function, not of different functions. Shared by different invocations of the same function and initialized only once. So it may be that you from main you call f returns, then you call g, then you call h, then again you call f, not recursively. Main calls f and then g and then h and then once again f. Then again this x value, whatever was earlier, like 6, it will stay. Okay. So this way you can actually pass certain information from invocation to invocation, apart from, of course, by passing arguments. But anyway, I will not discuss too much about static variables. If you are interested, you can look at our slides or consult any books. Okay.
Excuse me, sir.
Yeah.
So actually, I have used static variable, and I was doing a question. So in that question, I have to do in such a way that I have to call a function, and I have to return that in a main function. Then after again, I have to call a function. So then, will that static variable will change, or will again initialize to x equal to 5?
No, it will not be initialized. It will be initialized only once.
Next so after going to main.
Next time you make a call, it may be a recursive call or a call happening sometime after your first invocation. This value will stay. It will not be. But anyway, I do not think a static variable is a must for somebody to leave. If you want to use. I do not consider it a great feature of a programming language. If you want to use, but be careful how behave. And personally, I never use static variables because I think I can perfectly live without them. So static and global variables are not good. It's preferable to avoid for the sake of.
Sir, why global variables too?
No, let's take it for granted for the moment. I think I once explained, but anyway, let's not come to the debate.
Sir, what is the difference between global and static variable? Both serve the same function.
Both apparently looks like the same thing, but this static variable has a meaning only inside f. When f is not running, some g is running or h is running, x has no meaning. All invocations of the same function f can share this value x. But outside this function f, there is no existence of this x. Whereas a global variable is accessible from anywhere, whether it is f or g or h, unless that same name appears as a local variable in that function. Okay.
Okay, sir.
Okay. Okay, so if you're interested, you go ahead and read how to use static variables. I would say, I will not encourage you to use static variables. If for some reason you have an interest, go ahead and use it. Okay. And just a few, just one more point I would like to say. So these are called built-in library functions. You are already exposed to many of such functions. For example, you have seen printf, scanf. These are also functions. You didn't write it, but somebody wrote it for you. Okay. And when you compile, the bodies of these functions are included in your code. And anyway, these are basic functions. There are also other things like math functions. Like you can use square root, tan inverse, which is a10, exp, log, pow, and a variety of other functions are defined. So you look just at this header file math.h, abs, absolute value, and many other things. Okay. And also you have a list of string functions for null terminated strings. So they are usually declared in string.h. And that involves string length, string concatenation, string copy, okay, and so on. So our slides give you some exposure to these functions and how they work, what is the input-output behavior. So you can go ahead and check all these things. For me, it's a little bit boring to just reading some kind of a user's manual. You can see this is square root. This is tan inverse, arctan, exponential, e to the power something. Power is exponentiation, string length, string catenation. But how to use this thing? Please look at standard references like slides, books, notes, blah, blah, blah. Lots of things will be there. Yeah, so I think I stop about yeah.
Here log is natural log, sir. If we simply write log.
Yeah, no, what?
If we simply write log, then it is natural log or base 10.
I cannot really. If you simply.
Sir, you have written log. Is it natural log or base 10?
Yeah, these are the things. You should go ahead and look at some standard reference. I think this is natural log because log 10 is there. Log log10. Okay. So, but just yeah, read from the manuals and somewhere else. Okay. I think this is natural log. And there is something called log 10 for logarithm to base 10.
I googled it. It's natural log.
Please, I didn't understand.
Sir, it is natural log and log 10 is a base 10 log.
Log is base 10.
No, sir. Log is base E and log 10 is base 10.
Yeah, log 10 is base 10. That is obvious. Yeah. Yeah, that's what I remember. If I ever have to use it, I will just open one manual and find out which one exactly means what. Okay. It's good to be aware of the existence of these functions and from time to time use them. But anyway. Yeah, so that's all about functions that I wanted to cover. So after your midsem, we will start a new topic, whatever follows. The major things that remain are some pointers and dynamic memory allocation and what is that called? Structures, non-homogeneous.
So will you teach linked list?
When we talk about pointers and memory allocation, linked list will naturally come.
Okay, sir.
It's a natural example of dynamic allocation. So we will cover linked list. But I believe we have just 4 weeks or something like that. Somehow we have to finish without sacrificing much. Okay. Anyway, so let me stop with respect to this coverage, and then I just mention one thing. Yesterday, near the end, somebody talked about circular permutations. Now, this case is trivial without repetition. In fact, what you can do, you can always keep one particular element like 1 here, and then permute the remaining in all possible manner. Okay, this is just fix. In the case of non-linear permutation, we have also varied 1, 2, 3 up to n here, everything. It can start with this. But when you talk about circular permutations, you simply fix one or one particular element here and then permute in a linear fashion all the remaining elements, so that you get all of this n minus 1 factorial different circular permutations. So this code is fairly straightforward and obvious. Okay. So I initially, in the outermost call, I took I equal to 0. From main, but if I want circular, I will start from I equal to 1. Okay, so that's the only difference. The next question with repetition. This is still a big question mark to me. First of all, the total number of circular permutations with each repetition, you know, if there are n elements, the number of circular permutations is n minus 1 factorial. And if you also do not want to make a distinction between clockwise and counterclockwise things, then it is n minus 1 factorial by 2, right?
Yes, sir.
But if you allow repetitions in a circular permutation, we do not know any closed form formula. Okay. And we know certain series so we can compute things in some using some sums, and I mean actually the count of such repetitions, count of circular permutations with repetitions, but apparently there is no closed form expression. But what about a programmatic generation of these things? We do not have to compute the formula. As of now, I could not come up with a very neat way of doing these things. So one possibility is definitely generate all permutations. Okay, maybe fixing something at the first position, something like that, and remove repeated occurrences. I mean, repeated in the circular sense. This can definitely be done, and that will eventually give you the count also. Only thing is that it will require an exponential amount of space, whereas in our earlier examples, the space requirement was quite good, just a single array. Okay, and whether that can be achieved with a single array, it is still not clear to me. Okay, if I can come up with anything, I will let you know later, and I will post it to our course website. But this is definitely a way. Generate all possible permutations, maybe fixing something at the beginning, and then find out whether one permutation is already generated in the cyclically shifted form. If so, simply remove it from the list. Okay, but that's a I mean, with respect to space, that is not a good solution. Yeah, so that's all I had to say about these things. So, yeah, so I think this is all about the pre-midsem part. So if you now have any questions, please let me know.
Sir, 2D arrays will be there in our test?
No, of course not there. Oh, 2D array is another thing, right? We have to cover. Okay, okay. No, this will be the completely post-midsem thing. Yeah, 2D arrays is another thing we need to cover later. Yeah.
Okay.
Only one-dimensional arrays and only non-recursive functions.
So what will be the duration of the test?
We will actually let you know. Maybe around 1 hour, little bit more than that. And as we are thinking of, we will have 2 sessions, 5 sections in each session. So yeah, 1 hour, 1 hour 15 minutes, something like that. So that we can finish with comfortably within 3 hours total. Yeah, don't worry about these things. In a day or two, we will inform you everything about the logistic details of your midsem. Definitely by Friday. Yeah. So any other thing? If not, let us stop. Prepare for your midsem, and I wish you good luck. And really, I would like to say, please stay safe. Don't venture out. Okay, so
Thank you, sir.
bye.
Thank you, sir.